temperature, 100 Celsius in this case is water, and a similar behavior again. Okay? So I'm going to reach a plateau here, staying at fixed temperature while I continue to add thermal energy. At some point, the entire volume of water has boiled off, and it's become steam. And we're finally in the third and final phase here. And again, to exaggerate this, and these are not actually correct qualitatively, but it doesn't matter. You'll see I've drawn this with a different slope. Okay? So this would be a sort of generic expectation for some material as it goes from solid to liquid to gas phase, and how we expect the temperature to change as that is taking place. Okay? So important things to note during the phase changes. No delta T during the phase change. So that was somewhere down here maybe, at constant temperature. Okay. So those are the generic characteristics we should expect as we go through a phase change. How are we going to quantify it? Somewhat similarly to what we have over here. We're going to quantify it in the following way. And what we will say is simply that we can relate the amount of thermal energy that we're inputting into a system related to the mass by what's called the latent heat. Okay, so this now is the latent heat. This is quantity L. So our textbook may use some different language for it. Maybe not. Okay, so this is what we call the latent heat of transformation, perhaps. Now, of course, there's no delta T appearing in here because there is, not necessarily by definition, but by observation, no change in temperature as this is happening. Okay. So what we're going to find, as we saw for the specific heats, is of course we have different latent heats of transformation for different materials. And in general, we're going to have different latent heats as we go from solid to liquid, liquid to gas, or in certain rather rare cases, directly from solid to gas. Okay? So it's important to recognize that these are phase change specific. And that's pretty much all we need. Okay? Yeah.
Exactly is latent heat? Is it like it's not a change in temperature, but is it a unit of energy? Is it, or is it a constant during specific phase changes? And how do you quantify after a given amount of time? Because obviously with the other one, when you have delta T, it's also assuming, with constant heat transfer, you're implying that there's a given amount of time. How does that quantify? How do you relate that in this equation?
So, okay, so you kind of sort of concluded a little bit of that for yourself. So there's no temperature change here, so there's no temperature effect in this. Clearly it depends on how much stuff we have. So this is the amount of thermal energy needed to completely change the phase. So think of going from solid ice to liquid water. As you would expect, the more ice I start out with, so the bigger N is in here, the more thermal energy I'm going to have to apply to completely change the phase of that chunk of ice developable. And so this is material specific, but the only other thing it depends on is how much stuff I have. So what is it? I don't really know how to answer that other than to say, think about it, and we'll learn more about this on Thursday when we look at the microscopic picture. As you kind of know, as we go from solid to liquid phase, and much more dramatically from liquid to gas phase, our constituent atoms and molecules are generally speaking getting further apart. And so what's really going on here is that you need to input a certain amount of energy to overcome what I might describe as intra-atomic or intramolecular forces. In the case of going from liquid to gas, it's very clear what's going on there. You're basically totally breaking any bonds, attractive bonds between the atoms or the molecules. So that's where the energy is going. It's going at the molecular level to kind of break apart those bonds. So I'm not quite sure if that answered the various aspects of your question. Yeah. Okay, so conceptually I think really rather straightforward. What do I need to mention about this that I haven't already? A few jargon words. I think you know all of these. If I'm going from solid to liquid, obviously I'm melting. If I'm going from liquid to gas, obviously I'm boiling. Conversely, if I'm going from gas to liquid, I am condensing. And if I'm going from liquid to solid, I don't know, maybe I'm going to call it freezing. That's kind of slightly more material specific perhaps, but those are the sort of common terms you're going to hear here for these various phase transformations. The more rare one, anyone know the word associated with this? A lot of you do. Let's get somebody way in the back.
Sublimation.
There you go, sublimation. Okay. All right, so those are the jargon words associated with these different types of phase transfer. All right, so let me make sure one thing's clear about this. I didn't specify a sign here. That's maybe a little bit of an oversight on my part. Here, it's embedded implicitly, right? If I've got positive thermal energy going into some material, some system, the implication is that the temperature change is positive. Okay, so the sign is built in for us here. There's really no mention of sign here. And of course, if I'm talking about adding thermal energy, the expectation is that I'm going somewhere around in this direction, okay? I'm going from the solid to the liquid to the gas phase, or possibly solid directly to gas. So you may need to worry about an explicit sign in here. If I'm extracting thermal energy, of course, I'm going in the opposite direction. So I think the first thing I want to make sure you're taken care of here is as a sign. So take care of the sign. Okay? Don't overlook that. I'm taking out thermal energy during a phase transition. I'm going to the more dense phase, regardless of what we're talking about. And conversely, if I'm adding thermal energy, I'm going to the less dense phase. So that's an important thing to keep in mind when you're doing calculations. The other thing that we've embedded in all of this as an idealization, but one that's pretty much realized always, these processes are entirely reversible. Okay? I can add thermal energy, the temperature's going to go up. If I turn things around, pull that thermal energy out, the temperature's going to go down, linear dependence. Over here, I can reverse this fully also. So these are fully reversible processes, at least in our idealization. I'm going to ask you a slightly unfair question. I just want to get a sense of whether I should spend a couple of minutes doing a word problem. How many of you have seen specific heat and latent heat previously? Okay. I'm actually going to do this example because for those of you who haven't, I just want to make sure putting these two things together is a reasonable next step. So, fairly short example. It's going to combine both of these aspects. Once we're done, we'll turn our attention to a more detailed study of conduction and radiation. Okay, so here's the example. Ice at 0 Celsius is placed in a styrofoam cup. As soon as you hear that word or phrase, I want you to think about what the implication of that is. Containing 0.32 kilograms of lemonade. I'll assume is basically water at 27 Celsius. So there's the setup. After the ice and lemonade reach equilibrium, again, as soon as you hear that word or that phrase, think about what's underlying it. What does it mean? Some ice still remains. habit of doing a little bit of work with your neighbor. So let me just read this and I'm going to give you 2 minutes to work on it. Okay, so ice of an unknown amount is placed in a styrofoam cup containing 0.23 kilos of lemonade at 27 Celsius. That's 300 Kelvin, sort of it's the approximation I mentioned last week. What we often assume is room temperature, probably in a slightly warm room. After the ice and lemonade reach equilibrium, some ice still remains. The question is going to be trying to answer how much ice has melted. All right, so 2 things I want to ask in the class, and then I'm going to let you guys work on this together. What's the relevance of a styrofoam cup? Insulation. So I didn't mention styrofoam specifically last week, but you guys know why we use styrofoam. It's kind of, I don't know what it is, some organic thing, but it's a really good thermal insulator. So it's not something that tends to allow thermal energy to transfer across it. So this is going to allow us to assume that whatever this system is, namely the ice originally at 0 Celsius plus the lemonade originally at 27 Celsius, is thermally isolated from the rest of the world, okay? So we don't need to worry about complications of thermal energy going out to the rest of the world or coming in from the rest of the world. So, thermally insulated. What about the phrase reach equilibrium? What does that tell you?
The final temperatures of the ice and the lemonade.
Okay, good. So, final temperature of the ice and the lemonade are the same, so that's going to be an important constraint in this. All right. So those are the 2 things I just wanted to touch on. I'm going to let you guys spend 2 minutes, talk to your neighbor, how you're going to solve this, you can solve it, and then we're going to move on. So go for it. Yeah. A little louder? Oh, yeah. You need some numbers, right? So for water, so let me write this here. So L H2O, so this is going solid to liquid, is, let's see, 333 kilojoules per kilogram. Okay, there you go. So now you have the 2 constants that you need. Okay, 2 minutes. And talk to your neighbor. Introduce yourself if you don't yet know your neighbor.
But like the ice that melts, you can't just change it to water, you have to change it to water.
I know, yeah. So what you do is that goes to the ice. What's in the ice part is L, and a part of it is L. Part of it is but it's like the total sum of ice is absorbed. So you have to account for where it's going.
I mean, the 1% is weirdly 70%. The ice is like a natural form that still sees the ice. Is that don't we have things that are real one? Does that make sense?
Yeah. I get it.
So that just like conceptually kind of like
But I don't know how you're supposed to get it here. You don't have
but the final temperature of the ice is always going to be there. Like how's the final temperature of the
I think it's because like the energy is
Okay, I'm gonna give you about another minute.
so like something like it like got enough where it melted and excess.
You don't know what the units are.
Yeah, because it's like ice will stay at 0 Celsius. Like so it melts. Why don't it melt out water?
So like, can the final temperature be 0?
Would the delta T be
I think, okay, I don't, like, that sounds like, just by feeling it, it feels weird, but I think delta T is really all your I think you have 0 degrees.
still ice remaining, so it should be the same
Yeah, it can't be, yeah, so I think.
So it should be
Okay, so hopefully most of you found that not too challenging. How do we approach it? How do we solve it? And is there a key piece of information on here that tells us something important? Joseph?
I did have a question.
Yeah.
Because can we assume that at equilibrium they're both at 27 degrees Celsius because obviously the temperature of the ice increases and the temperature of the lemonade decreases?
Okay, I like your last phrase, but I do not like the original assumption, let me say. So I'm going to let you guys talk amongst, in the class context, talk amongst yourselves. Let's go there.
It says some ice still remains, so I just have to assume that at equilibrium, final temperature is 0 degrees Celsius.
Okay, so this turns out to be a key phrase. Okay, I didn't dwell on that when we introduced it because I wanted you to focus on it. Okay, so obviously we start off with a chunk of ice at 0 Celsius, and we embed it in some volume of water, let's call it, at 27 Celsius. So we expect, broadly speaking, the temperatures of those two materials to move towards each other. Thermal energy transfer from the warmer to the cooler object. Now, without knowing another piece of information, which was the source of a question at the front, just as you guys got started, we may not be able to do this, with the exception of the fact that we know some additional information. So we're told that some ice still remains. Well, the ice started off at 0 Celsius, so it can't get any warmer while still remaining ice. What does that tell you about the final thermal equilibrium temperature? It's still 0, right? That's the only way we can satisfy that criteria. Some of the ice still remains, it must be at 0 Celsius, but by definition it's in thermal equilibrium. So we know the final temperature is 0 Celsius. So that's the key thing we need to extract from this. All right, so that's the first place to spend some mental energy thinking about how this works. Now that we know that, how can we solve, and to some extent the next and last bit is kind of simpler, how do we solve the remainder of the problem? What can we say about an energy balance, so to speak?
So you know that wherever energy, so it's inside of the cup, wherever energy is changing in the ice has to be the same for the lemonade and the opposite. So, and you have all of the pieces to solve the equation for the lemonade, so you can do that and then switch this line. Use the L of the ice to then solve for how much ice there is.
Okay, I like that. So let me just paraphrase it and write it up on the chalkboard. Yes, what we expect is the thermal energy that is in a sense lost from the warm lemonade has to go into the increased thermal energy of the ice. So there has to be a balance there. And we know that we end up at 0 Celsius. The sign is different because in one case the thermal energy is being expelled from the warm lemonade, in the other case it's coming into the cooler ice. But in terms of magnitudes, we know it's the same. So in terms of magnitude, what I expect is to write, this is going to be a magnitude symbol, the mass of the ice that melted times the latent heat of water in the, wherever I wrote this here, solid to liquid phase. So that magnitude better equal, so what do I need here? I need the mass of the lemonade, I'm going to call it water for simplicity. I need the specific heat for water, and I need the delta T. And again, this is all magnitudes, so what do I know? I know this, 0.3 kilograms, I know this, I know this now because I know that I've gone from initial 27 Celsius to final 0 Celsius. So I know all of this, and of course I'm given this, so I can simply rearrange to say that the mass of the melted ice is this, I'm just going to take this over here for speed, is this divided by L over here, okay? So that's how I would solve this. So fairly straightforward, but it's nice that it combines a specific heat component, a latent heat component, and a little bit of thought about what this piece of information is telling us, and the embedded information in these two things, okay? So that's going to be a standard sort of framework for solving thermal energy transfer problems. In general, they can't get much more complicated than this, so it's just a question of being careful, making sure you understand signs where that becomes relevant. And I guess the one place where it's important is make sure that you're using the appropriate C's and L's. In general, they're different for different phases and different phase changes. Yeah.
So why do you use the Q equals ML equation for ice rather than the other one, the CM delta T?
Because we know it's changing phase, right? It starts off at 0 Celsius. It is most definitely a solid. That kind of defined it as such. But we know it ends up at 0 Celsius. So it's not changing. It's not changing. Okay.
So it's weird because it's like it says some ice still remains, so
Yeah,
that implies
fair
some
enough. Fair
melted. So I was kind of confused.
Okay. I mean, you know that the energy is going here to melt the ice. Once you've melted it, the melted ice remains at 0 Celsius, right? Because we know our final condition is 0 Celsius. So there's no component of the thing that I've erased now, the specific heat. There's no component of that for the ice that is melted because it just stays at 0 Celsius. Now, it's potential that you could have a more complicated problem where there are more different things.
So it's like the limiting case, like it's like just when it like melted, like just when it absorbed enough energy to change phase, and
That's
we
right.
stopped.
That's
Okay.
right. But of course, it could go beyond that, and then you have to fold in additional terms. Yeah.
What you have on the right there is the mass of the H2O. Is that just the 0.32 kilograms?
Yes. Yeah. Because remember, that is the mass of the water that is cooling down to 0. Yes, some of the ice is melted and it's become water, but it has not changed temperature. It's a little bit the same question you're asking. Sometimes you're going to have to factor that in as well, if beyond that it changes temperature. Okay, so you can sort of see it's easy to get a little bit tripped up here. Just try and be methodical, rigorous, and you shouldn't find it too difficult. Any other questions on that? Okay, so let me come back, and I'm doing a poor job this semester of keeping on schedule, but let me come back now and talk about our revisit to a more quantitative look at conduction, then a more quantitative look at radiation, and that might be as far as we get. So remember from Thursday, when we defined conduction, we talked about this without, requires a medium, but there's no bulk motion of the medium itself, unlike convection. So the medium itself is not moving, it's basically an increased excitation at the molecular or atomic level that's responsible for conduction. So conduction revisited, somewhat more quantitative now. So let's try and set up a kind of empirical or experimental setup. I'm operator drawing. Most of you know this, you were with me in the fall semester, so here's my best stab at this. Okay, so I've got a rectangular cross-section rod which is in thermal contact with two thermal baths. So, kind of lousy way of drawing this, but let me try and add some color here to represent what I'm trying to show you. So I'm starting off with a rectangular cross-section rod where the conduction is going to take place. On the left side, it's in contact with a thermal bath at a temperature TH for hot. And on the right side is in contact with a thermal bath, temperature TC for cold. Okay? So a thermal bath, as you'll remember, is defined to be a source of constant temperature. It's a, whatever it is, it's an idealized thing where it doesn't change temperature regardless of thermal energy transfer. It's a big reservoir, if you like. So let's see. I'm going to expect to have heat transfer along here, thermal energy transfer. And let's say that this rectangular rod has a cross-sectional area A. Okay. So this is the cross-sectional area A. Okay, so that's my experimental setup. As we've seen in many cases, we sort of look empirically to begin with and use that as the basis for defining a working equation. So empirically, what we will find are the following dependencies. First off, the amount of thermal energy transfer from the warm end to the cold end is proportional to the change in temperature between the ends. So let me just call this TH minus TC, for T hot minus T cold. We also find empirically that the amount of thermal energy transfer, that's proportional, is proportional to the cross-sectional area. We find that it is inversely proportional to the length, which I don't think I wrote on here yet, so let me go ahead and do so. This has a length from one side to the other of capital L. And lastly, if we're looking at this as a function of time, I'm kind of out of board space here, but let me just write it down here for completeness. I'll say this. It's proportional to the amount of time that I keep the system kind of in this situation. So the elapsed time delta t when there's a little t. So these are empirical observations, okay? Let me quickly recite them again, then we'll put them together in the form of a workable equation. The thermal energy transfer proportional to the temperature gradient, one end to the other. There it is. It's proportional to the cross-sectional area. It's inversely proportional to the length. And then finally, it's proportional to the time that we keep this system in this situation. So a lot of this, I would suggest, is very intuitive. And in fact, there will be some interesting parallels later in the semester when we talk about, let's say, electricity passing through conductors. There are some very interesting parallels there. So I'm going to take all of this together and see if I can build a simple equation that characterizes all of it. And so here it is. Take a look at this once you have seen it. Okay, so that's a pulling together of the various empirical observations we have. I put delta T down in the denominator on this side, so this is the rate of thermal energy transfer, as we expect. And then, as always, once we've got something like this, our next step is going to be to replace the proportionality with a constant. And so here it is. And that turns out to give us a pretty good idealization of thermal energy transfer via conduction in some material. So, do I need to say much more about this? Maybe not a whole lot. This is not surprisingly the thermal conductivity. Just in case you want to write this down for completeness, in SI units, this would be watts per meter Kelvin. Okay, hopefully that's clear. Watts per meter Kelvin. energy, watts,